adjacency matrix, and the number of walks of given links. Theorem. Let G be a graph with vertex set V of G equal to V sub 1, V sub 2, and so on down to V sub n, and adjacency matrix A. For each positive integer k, the number of different V sub I, V sub j walks of length k in G is the ij entry in the matrix A raised to the k power. Example, and we will use the same graph that we've used in the last video, and we determine the adjacency matrix. Remember that we have to think about the columns representing the vertices, and I've chosen the order A, B, C, D, E in alphabetical order. So the columns in order represent those vertices, and the rows in order represent A, B, C, D, E. And vertex A is adjacent to B, D, and C. So in the first row for vertex A, you see B, C, and D columns have a 1, and the other two are 0. Second row is for vertex B, and it has an adjacency with A, D, and E. Vertex C is adjacent to only two other vertices, A and D. Vertex D is adjacent to four other vertices, A, B, C, and E, but not itself, D. And lastly, E is adjacent to only two vertices, B and D. So we have our adjacency matrix, and if, for example, we would like to find the number of AE walks of length 3, we would take the matrix A and raise it to the third power, and then look at that position in the resulting matrix. But taking a 5 by 5 matrix and multiplying it by itself 3 times would take a lot of work by hand and probably result in a good bit of error because there's so much arithmetic in the middle of it. So we are going to find the number of walks of length 3 for each pair of vertices ij. So we will have to find a cubed, and we will use a TI-84 to find that power. So we're going to find A cubed. We've got our matrix A. Our first step will be to pull out our calculator and enter matrix A into the TI-84 calculator. To do that, we press second to get matrix, move over to the right to edit, and we'll select A to store our matrix. Our matrix is a 5 by 5. Notice I have to press enter as I enter numbers. Now entering the first row going across, 0, 1, 1. Each time I have to press enter, 1, 0. That's row 1. Now you see the blackened area has moved down to row 2, so I enter 1, 0, 0, 1, 1. Notice we can't see the whole thing in this form at once either, so it's easy to make a mistake. We have to be very careful. 1, 0, 0, 1, 0. Row 4, 1, 1, 1, 0, 1, and last row 0, 1, 0, 1, 0. Then I do second quit. Now, just to be sure I've entered this right, I want to get the entire matrix printed to the screen so I can look at it carefully. Second matrix, this time I just select the name A, and if I hit return, it'll print it. And I verify that each row is correct, and it is. So now I want to find A raised to the third power to find how many walks of length 3 there are. So I do second matrix, I select A again, but this time I say raised to the third power, just like you would a number. This is defined in the calculator, and press enter. And there is the matrix A cubed. So I make an image of that on the slide, and there's our A cubed. So, for example, if you look at the 4 in the first row, first column, that would tell us that there are 4 walks of length 3, because we did A cubed, the exponent is a length, between A and itself. Well, what are those 4 walks? Well, the matrix tells us how many, not what they are. From A to A of length 3. Well, it could be A to C to D to A, that's length 3. Or it could be A to D to C to A, that's 2. A to B to D to A is 3. And A to D to B and back to A is 4. Let's see what else. If we look at the third row, second column, there's a 3. This tells us that there are 3 walks of length 3 from C to B. Start at C and go to B. There should be 3 walks of length 3. So C, D, A, B, that's 1. C, A, D, B, that's 2. C, D, E, B, that's 3. That's the third walk of length 3. And finally, we will get back to what it means to be connected. Definition. A graph G is connected if for every 2 vertices, U and V, G contains a UV path. If G contains a UV path, then we say U and V are connected in G. That is, G is a connected graph if every 2 vertices of G are connected. Example. The graph on the left is a connected graph. We can start at any vertex, A, B, C, or D, and find a path to any of the other 3 vertices. The graph on the right is a disconnected graph. If we start at vertex A, there is no path to vertex E. Definition. Let U and V be 2 vertices in a connected graph G. The distance d of UV from U to V is the length of the shortest UV path in G. Looking at our connected graph on the left, to find the distance between vertex A and vertex C, we could start finding all the paths between A and C and then see which is the shortest. One of the paths would be A, B, D, C. That is of length 3. Another path would be A, D, C. That's of length 2. Another path would be A, C, and that's of length 1. There are a few other paths there, but the shortest path is the path AC, which is of length 1. So the distance between vertex A and vertex C, D of AC, equals 1.